Hi everyone, welcome to the Earth Science Regents Review podcast series created by Hammock's Middle School Earth Science Department. Today we're going to talk about weather fronts. Well, before we get into fronts, we've got to talk a little bit about clouds first. Clouds form when warm air is going to rise. As warm air rises through the troposphere, it's going to cool off. But due to the lack of pressure, the air mass is going to expand. So it's a special type of cooling called expansional cooling. It's going to cool to the dew point, and at that dew point you're going to get cloud formation, condensation, and inevitably you'll get some precipitation as well. Well, clouds just don't form in thin air, they have to form on a surface. Now, dust, pollen, pollution, whatever little objects you have in the atmosphere, water droplets can condense onto. Those are what we call condensation nuclei. Now, clouds are made up of billions upon billions of water droplets with condensation nuclei at the very center. So you can see the average size, they are really, literally microscopic pieces in the atmosphere. Now, warm air, we had mentioned, rises. Now, there's three different ways in which it can rise. The first way is what we call orographic lifting. Sometimes warm air masses are going to come off the ocean and they're going to come in contact with the mountain range. The easiest way for an air mass to go around a mountain range is to go up and over it. Well, again, because of the fact that it's cooler in the upper atmosphere, your air mass is going to condense at the dew point, and that's where you're going to get your massive precipitation. The side of the mountain that gets precipitation is called the windward side of the mountain. That's going to be the wet side. And that's all caused by, again, that expansional cooling in the upper atmosphere. Well, once that air mass drops off all of its moisture on the windward side, it's very cold and dry now. So it's going to descend down the leeward side of the mountain because it's a little bit more dense now. As it sinks down the leeward side of the mountain, it starts to heat up because the pressure is starting to become greater as you travel down the mountainside. That's what we call compressional heating. Now, because the air mass is so dry, we say that the leeward side of the mountain has what's called a rain shadow effect because of the number of deserts on the rain shadow effect side of the mountain. Then we call that the leeward side. So you look at the diagram, left side of the mountain is the windward, the right side of the mountain is going to be the leeward. And again, you see the cloud formations that are formed due to this orographic lifting. The second way is through convective lifting. And by now, you should have an idea about what convection is. It's all about density differences. Warm air rises and cold air sinks. And this constant circulation now is what we call convection. If you're not sure, please check out my other podcasts in this series because we do get into a little bit more detail about what convection is all about. The third way is what we call frontal wedging. And this is when a warm air mass and a cold air mass are going to collide with each other. Anytime there's a little struggle between them, warm air always loses and gets forced upward. And again, it's going to cool to the dew point, clouds and precipitation form at the point where frontal wedging actually occurs. Now, there are some different air masses within the continental United States and North America that are going to collide with each other and interact. You have empty air masses, which are maritime tropical. You have MP air masses, which are maritime polar. CP or CA air masses, which are continental Arctic or continental polar. And then CT air masses, which are continental tropical. Notice that some are wet, some are dry, some are hot, some are cold. You definitely need to know the characteristics. Now, each air mass gets its own individual characteristics from the source region in which it comes from. So if your air mass forms over the Pacific in the north, it's going to be maritime polar. If it forms over Canada, continental polar or continental Arctic. Forms over the southern Pacific, Gulf of Mexico, or southern Atlantic, maritime tropical. Or in the continental U.S., around the Four Corners region or Mexico, continental tropical. So very important to understand the source regions in which those air masses come from. So basically, a front's a boundary between two air masses. And we have cold, warm, stationary, and occluded. And what's important here is that each front has its own individual characteristics. Please notice the symbols. They're actually in page 13 in your reference table. The symbol itself is going to tell you the direction of motion. Cold, occluded, warm front, those are no problem because they're actually moving in some sort of direction. Stationary front, they don't move because you get air masses colliding with each other in opposite directions. So let's start out with the cold front. This is where a cold air mass is trying to overtake a warm air mass. What happens here is that you tend to get very heavy precipitation, tornadoes, you tend to get thunderstorms, very simply because you get a very quick change in the atmosphere. Cold fronts travel very quickly, so they force that warm air up so rapidly, condensation is so violent, you get that nasty precipitation right at the frontal boundary. Once that air mass travels through, though, you get higher pressure, cooler temperatures, and much, much drier air. So you can see that here's your highlighted region for the front. Before the front, you have the warm air. Behind the front, you have the cold air. The boundary, you notice it's a very steep boundary, which represents you have a very, very quick change in atmospheric conditions. The rapid condensation, the rapid lifting of the warm air, dramatic precipitation right at the frontal boundary. Warm fronts are the exact opposite. Here's where a warm air mass is trying to overtake a cold air mass. You tend to get gradual precipitation. Usually occurs over a couple days. So if you tend on getting a warm front on Wednesday, you're going to get precipitation probably Monday night into Tuesday. Very gradual precipitation because the warm air lifting is not as violent. Once that warm air mass passes through, what's going to happen is you're going to get lower pressure, a little bit warmer temperatures, and a little bit moister air. So you'll see before the front you have the cold air, behind the front you have the warm air. Here's your frontal boundary there. You'll notice that the precipitation occurs before the frontal boundary actually comes through. Very slow, gradual precipitation. So there's your cold front on the left. You'll see the cold air is going to be coming down from Canada. So you see the temperatures in the 20s, the 30s, the 40s. You see the warm air mass is traveling in a northwest direction. And what's going to happen here is your warm air in the 60s and 50s are going to be traveling in a northwest direction. The reason why they're traveling like that, because low pressure goes in a counterclockwise rotation. Occluded fronts, or your mid-latitude cyclones, this is where your cold front and warm front actually meet up with each other and they merge together, they zip together. You are going to get major, major precipitation with these types of storms. And what's going to happen here is when you look at a satellite image, you're going to notice a mid-latitude cyclone because of the classic Kama cloud. And you'll notice in this picture from 1998, the classic Kama cloud extends from Minnesota all the way down into the Gulf of Mexico. Now, on the left-hand side, that is your mid-latitude cyclone. On the right-hand side, that's your occluded front. The mid-latitude cyclone hasn't zipped together yet. The occluded front, it has zipped together. That's why you have the purple head to that specific front, because you see the merging of the warm front and the cold front. Now you see here, the cold air is on the left. The cool air is on the right. The warm air is in the middle. The cold air catches up to the cool air, forcing that warm air up very rapidly, and you get a significant amount of precipitation with that rapid rising of warm air. So again, you can see on the left-hand side, that's a mid-latitude cyclone about to zip together into an occluded front. There's the temperature between the cold front and the warm fronts. So you see the big major warm sector there. And in this picture, you can actually see the occlusion that is actually taking place. The last type of front is what we call stationary front. And this is where warm front and cold front is going to collide together. They kind of battle for supremacy, so they kind of stall out and they don't move until one of the fronts actually weakens out. And you tend to get a little precipitation here because warm air does rise up a little bit, but they are a little bit battling here for supremacy of the area. So you'll see that the picture on the left shows you the stationary front symbol. On the right-hand side shows you what it might look like from the side as well. And again, here's a weather map that just gives you an idea in terms of where a stationary front might be located and the different characteristics with it. So with that being said, that was a quick tutorial on some of your weather fronts. Please make sure you understand the characteristics of them. Please make sure you go out and you practice your weather maps and know how to forecast, because when it comes regions time, a lot of your questions are going to be related to weather maps themselves with mid-latitude cyclones or occluded fronts on them. So please make sure you know that. So that's it for now. Thanks for joining me, and we'll talk to you soon.